Okay, chapter 20. Before we start this, just want to remind you, we've been working with box models. Let's say we have a box and inside it we've got a 1, a 2, and a 3, and we draw from that box, let's say 100 times, and then sum the results. From that, we can estimate what the results will show if I draw 100 tickets from this box with replacement and then add those 100 tickets. I can guess what the sum would be by figuring out the EV sum, the expected value sum, which our formula for that was the number of draws, which I just remembered I need to add that to our formula sheet. Let me write myself a note here real quick, because otherwise I won't remember. Okay. Update formula sheet. Okay, so it's the number of draws times the average of the box. And remember, you can find that by doing one of our stats, or just by doing 1 plus 2 plus 3 and dividing by 3. And then there's also a formula, SE sum. And that is the square root of the number of draws times the standard deviation of the box. And again, that standard deviation can be found by putting these numbers into a list, 1, 2, and 3, and then doing one of our stats with it. So these are formulas we've learned for expected value and SE for sums of boxes. We're now going to talk about these formulas for percentages and for averages as well, and we'll be doing that in chapter 20, 21, and 23. So, chapter 20, we're going to get the EV percent and SE percent, and then chapter 23, we're going to get the EV and SE average. Okay, in 1860, Abraham Lincoln, Republican, ran against 4 other candidates. Lincoln received 40% of the popular vote. The strongest challenger was Stephen A. Douglas, who received 21% of the popular vote. So what we're going to look at is Douglas, the percent of votes he got. So we've got this box, and in this box we have Douglas, and he received 21% of the votes. So we've got Douglas. I'm going to assign him a 1. And then since he received 21% of the votes, I'm going to say he has 21 of 100 tickets. So the other 79% were votes for other candidates. But we don't care about those other votes. We're going to assign a 0 to them. So 1 is Douglas, and then 0 is Lincoln. Sorry, there were 5 other candidates. 5 total. So these other 4, if somebody voted for them, their vote doesn't count in this example because we're looking specifically at the outcome of Douglas votes. So, in 1860, we've got 21% of the popular vote went to Douglas, 79% went to the other candidates. What is the histogram for the percentages of Douglas voters of a sample size of 20? So, let's talk about this. So, using sampling distribution, we can answer questions such as, how well will a sample size of 20 estimate the percentage voting for Douglas? And Douglas received 21% of the popular vote. So with sample size of 20, how likely is that sample? Is it that sample would show that Douglas received 35% or more? And what I really want to focus on is the second question. Back to this question, the histogram is going to be approximately normal. 20 is a pretty small sample size, so it might not be exactly normal, but it's going to be close to normal. A sample size of 200 would be better, but since it's a simple random sample, that's what SRS stands for. It's approximately normal, so we can do EV sum and SE sum, or sorry, EV and SE percents with this, and then shade norm to answer this question. So to get that sample of 20, they randomly select 20 of the voters. So out of the, how many total voters were there? If you take the sum of all these voters, if we randomly select 20 of them from all those voters, so we're randomly selecting 20 and then count how many of them were Douglas supporters. You can get the sample percent, and that's called the statistic. And then if you do it over and over and over again, you'll find it's pretty close to 21% when you look at all of the samples taken. So here's our normal curve. Not exactly normal, but pretty close. This is the formula, except we're going to simplify that formula down for SE, and this is the formula for expected value percent. So this shows us two new formulas here. EV percent, that is the given percent or parameter. So we are given 21%, not parament. And the SE percent is this formula down here, but a simpler version of it is sorry, trying to simplify this down here. It should have there it is. Okay. SE sum divided by the number of draws. Whoops, divided by the number of draws. Times 100%. And then we have this thing right here, SE sum. So that's saying the SE sum of the tickets. The easiest way to calculate this, you can use one of our stats if you want, but the easiest way is to just do the square root of the percent of ones as a decimal. So I'm going to say percent of ones, but you have to change it to a decimal, times the percent of zeros. Okay, so I just threw to put an L there, that's fine. Just threw these formulas at you. I want to show you how to use them and then how they're basically the same as EV sum and SE sum when you're working with them. So if you remember from chapter 17, EV sum and SE sum, we worked with those to calculate percent of different events happening, the probability of them happening. So we went down through shade norm, and we're going to do the same thing with these two, and then with EV and SE averages as well. So let's look, if we increase the sample size to 40 voters, here the SE was 9.1% and 21% when we had 20 voters. So 21%, give or take 9.1%. When we increase it to 40 voters, it's 21%, give or take 6.44%. So increasing the voters gets rid of some of the variability. That's what this SE percent is. That's like your standard error. That's how far off you're going to expect most people to be from the average. So this error is smaller when we have a larger number. And then if we increase it to 400 voters, the expected value is still 21%, but the SE is now only 2.04, so it's give or take 2.04%. So the moral of the story with these last few slides is we have formulas to get the expected value in the SE percents. And the bigger your sample size is, the smaller your error, your standard error is going to be. So you want big sample sizes whenever possible. And that's what this says. You can see the normal curve on these ones, how close this is to actually normal, except it's really tall, but there's very few spaces not filled in here. You can't even really see the spaces that are not filled in there. Versus here, we've got an area right here that's not filled in, area not here filled in, area not here. We've got these areas outside the curve. So bigger sample size is better. That's the main thing to say there. Bigger sample size equals better. Okay, the expected value is, there's this fancy formula for it, but it's really just the population percent or the parameter given. So it's the percent or parameter given. And then SE sum is, SE percent is this formula. And furthermore, we can take it to be this formula. So there's some fancy math going on there, and it's going to be that formula. So instead of using this one, this is going to be the simplest formula for us to use. The standard deviation of the box, you can get it again using one of our stats, or you can do the square root of the percent of ones times the percent of zeros percent as decimal. That's probably still a little bit confusing for you as I write that, so I'll show you what it's meaning here. We'll do some examples so you can understand what that's saying. In a population of 100,000 people, so there's our number of draws, we know that 20,000 are minorities. I take a simple random sample of 400. Oh, I'm sorry, that's not the number of draws. The 100,000 is the population size. The number of draws is a sample size of 400. So this is number of draws. And I want to know how many minorities I would expect to get from the sample, and I need to find the standard error. Okay, this doesn't have any percents in it. If you don't see percents, you're not going to use percents. We're going to use EV and SE sum on this one. And I know that because it's asking how many. If it says percent or averages, you're going to be doing something different. But if it just says how many, it means sum. So it's the formulas we already know. So EV sum and SE sum. Well, we would expect to get 2 or 20,000 out of 100,000. So we can change that to an EV sum by making a box. And I'm going to get rid of some zeros here. And I'm going to say there's 20 ones and 80 zeros. You can say 20,000 ones and 100,000 zeros too. That's fine. It really doesn't matter because it's proportional. It's at the same ratio. Then you can type into one of our stats. So type into your list. We're going to do frequency list. So list 1 is 1 and 0. List 2 is 20 and 80. So let's go to my calculator and into list, edit. Let's clear out what's here. And type 1 and 0 and 20 and 80. So the 80 comes from 100,000 minus 20,000, and then I just cut some zeros off there. And then we need to do stat, calc, 1-bar stats, tell it we have a frequency list. And calculate. Okay, so the average is 0.2, the standard deviation is 0.4. Nope, sorry, wrong one. Okay, formula for sum is the number of draws, 400, times the average of the box. SE sum is the square root of the number of draws times the standard deviation of the box. So that is 400 times 0.2, 80. Or if you think about it, 20% of 400, because this is 20% of the total. So 20% of 400 is 80 people. Will be minorities. That's our expected. Give or take the square root of 400 times 0.4. So give or take 8. So we're going to say 80 people, give or take 8 people. Then it says what percentage of minorities do I expect and what percentage for standard error. So it says find the expected value, percent, because it says expect percent, and SE percent. So this is where we're going to start using our new formulas. EV percent is the percent of people from the population that are minorities. So 20,000 out of 100,000 is 20%. If you don't know how to do that, easiest way is to cross off some zeros. Whoops. That didn't work. I crossed it off in the wrong order. It's 20 of 100. 20 of 100 is 20%. Or you can do 20,000 divided by 100,000 and move the decimal over twice. Either way works. Okay, SE percent is this formula. The standard deviation of the box over the square root of the number of draws times 100%. And we're going to use this formula for the standard deviation of the box. So we're going to do the percent of ones. Well, there's 20% that are minority times the other 100%, or the other part of that 100%. So 20% minus 100% is 80%. So we got 0.80 by doing 100% minus 20%, and then moving the decimal over twice. Divided by the square root of the number of draws and then multiply whatever that is by 100%, or just move the decimal over twice. So let's do that. Square root of 0.2 times 0.8 times the square root of 400. Actually, is it the square root? Yes, it is. The square root of 400. And then times that by 100, and we get 800. That's not accurate. Why is that not accurate? Hold on, I just made a simple mistake somewhere. Let me figure out what my mistake is so we all never make the same mistake. Chapter 20. Okay, it should be 2. Oh, I know what it is. I multiplied instead of divided. So it's 0.4 is 0.2 times 0.8 square rooted, but you'll notice that's what this number is too. divided by the square root of 400 times 100% gets us 2%. So this is saying 20%, give or take 2%. This and this are identical. One's just an actual number of people, one's in percents. 20% of 400 people is 80 people. So these are doing the same, getting the same results. It's just a matter of, are we looking at percents or are we looking at sums? Okay, now we need to find the SC percent for a sample size of 100. So SC percent is 0.2 times 0.8 square rooted divided by the square root of the number of draws. And the sample size of 1600, we also need the SC percent for that. So we're going to do square root of 0.2 times 0.8 divided by the square root of 1600. Okay, I'm going to type both of these in. So 0.4 divided by 10 is 4%. But then we need to multiply this by 100 to get 4%. And this will also multiply by 100% to change it to a percent rather than a decimal. 1%. Okay, with a sample size of 100, we had a standard error of 4%. With a sample size of 400, we had a standard error of 2%. With a size of 1600, we had a sample error of 1%. So again, this is just drilling home the fact that bigger sample size is better. You're going to have less standard error or less error in general for that sample. Okay, this is just saying we can do the standard normal z-score with percents, just like with everything else, and the 68, 95, 99.7% rule still applies. So, still dealing with this data, 20% minority, give or take 2%, or 80, give or take 8. It says, would we be surprised if we got 75 for a minority? Nope, that's within one standard error, because 80 minus 8 is 72, 80 plus 8 is 88. So, nope, that is within one standard error. And remember, standard error is basically standard deviation. Okay, then the next one is asking percent. So I went with 80 give or take 8 because it didn't have percent. So I was just referring to the raw numbers. This one does have percent, so we're referring to the 20% give or take 2%. So one standard error away is going to be 18% to 22%. Two standard errors away, if we go out another 2% from each of those numbers, 16% to 24%. And three standard errors is 14% to 26%. So three standard errors is our gray area where it's almost surprising, but not quite. So you've got a couple options here. You can say it's almost three standard errors away, so that would possibly be surprising. Or you can say it's within three standard errors. So no, I'm not surprised. Your choice on how you want to word that. Both of those are considered acceptable as long as you include the fact that it's almost three standard errors away. Okay, in a certain town, 25% of college students own an automobile. So there's our parameter given. 25% of all college students in that town own an automobile. If we take a simple random sample of 400, so that's our number of draws, what is the chance that less than 20% of the sampled students own an automobile? So this is asking for a chance of some percent happening, some percent of something happening. So that means we're going to use shade norm. So let's start with step 1. Remember, we had 6 steps here. Step 1 was to write down the average of the box and the standard deviation of the box. Okay, the average of the box isn't so important. I'm just going to write down that it's 25%. You can also have it as nope, wouldn't be 0.25. It's 25% of the 400, and I'll show you why that's not important here in just a minute. So I'm actually going to just cross this off as well. The standard deviation of the box is the square root of the percent who do own the car times the percent who do not own the car. 75% comes from 100 minus 25%. So if I do the square root of 0.25 times 0.75, I get 0.433. So I'm just going to do 0.43. Step 2 is the EV percent and SE percent. Okay, EV percent is 25%. You don't need the average of the box to get that percent, and that's why I crossed the average of the box off, because it's simply the parameter given this 25%. The SE percent is the SD of the box, so that 0.25 times 0.75 divided by the square root of the number of draws times 100%. So this was 0.43. Do 0.43 divided by the square root of 400 times 100%. We get 2.15%. That means when we draw a sample of 400, we would expect 25%, give or take 2.15% of the people in the sample to own a car. Okay, step 3. Oh, you know what? This was actually step 2, and this was step 3. I knew I was off. So we're actually to step 4. Step 1, not as important with percents, but it's 25% do own a car, 75% do not. Okay, so that was step 1. Step 2, step 3, step 4 is draw a normal curve. So we expect 25%. That's right in the middle. It asked 20% or less. So I'm going to draw that down here and shade underneath that. Step 5 is Z-score. Well, we want to look at 20%. We're expecting 25% over 2.15%. And they're all percent, so you do not have to change them to decimal. Since they're all in the same unit, they can stay that way. Okay, that is a Z-score of negative 0.23. So then we do shade norm. Is that really just negative 0.23? No, it's not. It should be negative 2.3. So we're going to do shade norm. Negative 10 to negative 2.301. Remember, to get to shade norm, you do second vars, arrow over to draw, and then type in your numbers. It looks like that is 1.1%, approximately. Wow, that's small. So the chance of less than 20% of the sampled students owning an automobile is like 1% chance of that happening. It's pretty small. Okay, so that is sampling with percents and doing EV and SE percent to get to answers. It's the exact same steps as EV and SE sum. It's just now you're dealing with percents, so you have different formulas for EV and SE. Okay, this, I see this on quizzes and tests a lot. This seems to be, Kimberly Hatfield is the one who writes the final. Seems to be one of her favorite questions. For simple random samples, the accuracy is determined by the sample size itself, not the sample size relative to population. So if you want the same accuracy in Salt Lake and Logan, we should sample the same number of people in Salt Lake as we do in Logan. And that's the case even though Salt Lake is I was going to say a million times bigger. We'll just go, it's much bigger than Logan. You get the same accuracy if you sample 200 people in Logan as 200 people in Salt Lake. And accuracy is referring to standard error size. And that's because the standard error is the standard deviation divided by the square root of the number of draws. So that standard error formula doesn't take into account the population size. It just takes into account the number of people you sampled. Okay, so I'm interested in estimating the percentage of people who watch Channel 5 News. In each case, will Logan or Salt Lake City sample be more accurate? Sample 500 Logan, 500 Salt Lake. There should be an option C on this where it's the same accuracy. Okay, I sampled 500 Logan, 750 Salt Lake. I sampled more in Salt Lake than Logan, so it's going to be more accurate. Sampled 5% of Logan residents versus 5% of Salt Lake residents. Logan's smaller than Salt Lake. Since Salt Lake is bigger, 5% of Salt Lake is a bigger sample than 5% of Logan. So Salt Lake is bigger. So bigger sample size means more accurate results. It does not matter how big of a population you're pulling that from. And I don't want to do this example. Okay, I do want to do this example. So suppose it is true that 50% of young mothers say that finding childcare is a problem. A childcare referral group takes a simple random sample of 450 young mothers. Okay, so we have 50%. That's the parameter given. So clear down here on step 3, I already know EV percent. 50% is what we would expect. Our sample size is 450. We need to create a box model and then find EV and SE percent. So a box model, when you're dealing with percents, a box model is just either it is or it's not. It is 1, 0 is not. So 50% say they have a hard time finding childcare. 50% say they do not have a hard time finding childcare. Step 2, we don't need the average of the box because the only reason we calculate the average of the box is to get the EV, and we already have the EV percent. We do need the standard deviation of the box, and that's this cool fancy formula, 0.5 times 0.5 square rooted. So I just take the numbers from the box and change them to decimals. You can calculate this using 1-bar stats as well, where you do a frequency list of 1 and 0 and list 1 of 1 and 0, and then the frequency of the percent and percent of ones and percent of zeros. I just find this formula to be quicker than typing into 1-bar stats. So if we do the square root of 0.5 times 0.5, that is 0.5. So then the standard error percent is the standard deviation of the box divided by the square root of the number of draws times 100 to change it to a percent. So we get 2.4%. Okay, that means we expect 50%, give or take 2.4%. When we sample 450 young mothers, that's what we expect for what percent of them have a hard time finding childcare. So like that's babysitters, daycare, that kind of stuff. Calculate the chance that more than 50% of the mothers in the sample say finding childcare is a problem. Well, we already did steps 1, 2, and 3. Here's our results, so we're ready to move on to step 4. Draw the normal curve. 50% is in the middle. 53% is what we're looking at, and it's more than that. Okay, step 5. Is z-score. We want 53%. We expect 50%. Give or take 2.4%. And these are all percent, so you do not have to change them, as I said a few minutes ago. Whoop. Where is my calculator? Sorry, I picked up my phone for my calculator for some reason, and then I had to find the calculator. Okay, this is 1.25%. Actually, sorry, a z-score is not a percent. It's just a raw number. The percent cancels because this is 3% over 2.4%, so the percent cancels each other out there. Last step is shade norm. We're doing 1.25 or more. We're going to type that into shade norm. And well, I tried to fix that. It doesn't look much better. The answer is 10.6%. So that's the chance that 53% or more of the mothers in that 450 person sample do have a problem finding childcare. Okay, here's your homework. Except I'm certain I shortened that. It is due Friday, May 1st. And the shortened assignment is, okay, this is chapter 20. Set A, numbers 1 through 3. Set B, number 1 through 3. Set C, number 1, 3, and 4, and review 3, 6, and 7. So I didn't shorten that one much. Let me know if you have questions.